between the new file format and the old one, but it's only the compression algorithms that have changed. So when the antivirus software was scanning this, they were at the first file and saw the compression algorithm they don't support and just skip over the whole archive. Now we came to RAR file format, and this is an interesting one because the first file block inside the RAR file format defines the whole archive. It says if it's a multi-volume one or stuff like that. But it has a pretty neat feature that you can use to declare a block as a temporary one. So next time you add an archive to that particular, add a file to that particular archive, that first block will be stripped. And since it is stripped, the archive is broken. So you can use this as prevention of modifying data. We will show this in the demonstration later. But what the problem was is that the first 8 bytes are used to identify the archive itself, but the next block itself is pretty much standard. So our best guess is that some of that data was used to identify the file format, and that's why the scanning didn't work properly. Now, of course, just as a zip, we tried password protecting the single file, and it also worked. Now, every file inside the zip, inside the RAR archive also has a version requirement for the software to extract it. And by setting the version requirement to 25, which is the FF and hex, we were successfully able to prevent some software vendors from decompressing such archives. Of course, the first file cannot be decompressed by any of the software that processes RAR archive, but the rest of the files in the archive work just fine. Now, cap file format. What we wanted to do is see if we could increase the compressed file size. So we set that size to 4 gigabytes, which is the maximum file size allowed by the cap file format. And this doesn't do anything for the cap processors because they don't rely on this information when they're creating the file. They're just decompressing data, and once they come to the terminator byte, they know the output file size and they just write that. But if somebody was to try to allocate all this data, of course their archive processor would break or just skip over the file thinking it's too large to contain any kind of malware and just skip scanning it. Now for gzip file format, we just added the documented extra field. It's in the documentation, and it's really not commonly used, and that's why some software vendors had the problem of finding the start of the compressed data, which was shifted by a few bytes, and that's why the decompression didn't work. Now for 7-zip, it has also, just like RAR archive, it has several blocks which describe the following content, and by setting the CRC of the header to an incorrect value, you would still have a valid archive which can be decompressed by 7-zip, but some security vendors were checking the CRC and telling, oh, this file is broken and we're not going to scan it. Now, this can be implemented like this. So, first header, which has these 4 fields, can be set to 0, and this only works if you have a single file in an archive, because then 7-zip will generically try to locate that particular compressed file, and it will succeed at that, and the other archive or processors found in security software wouldn't. Now, what are the conclusions of our testing? Files can be malformatted to carry hidden payload, and that hidden payload can affect the way we process archives, and in case of security, we won't be able to scan the whole archive. Now, malformatted files can also be automatically fixed, or by adding a generic decompression routines to the archive processors, such as WinRAR has for zip file format. They can still be decompressed even though they don't look valid from the documentation standpoint. Now, of course, files can be malformatted to carry additional steganography content. And this hidden content has a self-destruct button. So if you are not careful enough in the process of repairing an archive or modifying anything, you would end up with losing the important data. Now, That brings us to our first demonstration. We're going to do some hex editing. We're going to hide existing files inside a zip archive. We're going to insert some hidden messages. We're going to invent our own file format, and we're going to show off the tool we used to check all this, and it's going to inject some Stego data inside an existing zip archive. So let's do that. Okay, so the first thing is we wanted to show is this particular RAR archive, which is the first VSA security advisor we posted. So it only has one particular file in it, and it's malware.bin. It's compressed configure sample, I believe. So its header is damaged, and you can see that just by looking at the hex output. As you see, first 2 bytes are zeros, and they're supposed to be the format signature, which is for zip pk. We damaged that intentionally, and at the end, we added another file which is hidden, and you don't really see it. It's called zip insider. If you see that string right here, and since that file is hidden and it's not shown in the archive processors, that actually confused security software and thought that the archive was broken and didn't scan it in full. Now, some other fields were modified here. We're not going to go into that. This was documented in our white paper. Now, a tool used to create such an archive is called Zip Insider. We made such a program to test if we are correctly looking for the Stego content and if we are processing these archives correctly. Now I'm going to demonstrate how it works. The archive in question, this one, Riddle, already has a hidden content inside it. So just by calling Zip Insider, we can list all files that are hidden inside that particular archive. Of course, I've removed the hiding. So hide Riddle. Okay. Now we see that we have found one file that was hidden. It's called file. It doesn't have an extension. Its size is 103 bytes. Has a certain CRC, of course. Now, that particular file is now hidden in the archive because the process was reversed. And if we wanted to show that particular archive, we would modify the archive itself in order to show that particular file in any program. So now we have modified the archive, and we can see that file. And that file is particularly a text file, which says the answer to the hidden riddle is the riddle itself. You have to look closer to find your answer. This isn't the answer to the question why this file is so special. And I actually sent this to a couple of my guys, and they were able to find this file, but the rest of the puzzle was beyond them. So this was an example of hiding existing content inside an archive, but we have also injected additional content inside the archive itself. So if we use extract to get that new content to the disk, file has been successfully extracted to the disk, and this is that injected content on the disk. As we see, the file is password protected, and it's another text file, and the password for it is, of course, riddle. And this is the answer to the question why this file is special. Is because we made it with the tool called Zip Insider. So as you can see, data can successfully be hidden inside an archive, and we can do all sorts of stuff with our tools to extract them back. Now, provided this particular tool both hides and reveals content, so it's only aware of its own mechanisms for hiding additional data. So we're going to talk about how we can generically detect any kind of hidden content a bit later, but